So goal of today is to understand how cloud computing can be used to solve big data problems. So till now we were trying to understand how cloud computing can host web application. So web application is one of the application model which is very popular in cloud computing discipline. But other application model which is very popular is big data analysis, which is based on MapReduce and Hadoop. Of course, as I said in my lecture 3, there are almost 19 types of application that works on cloud, but these are the top 2-3 ones that is very popular. We also have application like content delivery networks on which systems like Facebook is based. We also have applications like stream processing like Facebook and Twitter, which is also running on data centers. There are many applications, and some of those applications you will learn in the big data module, which comes in the next semester. But in this one, the main goal was to teach you the fundamentals of cloud data centers, application orchestration, and somehow relate that to web application that we studied till now, and then also relate that to MapReduce and Hadoop. And the idea is that rest of the application model is stream processing, NoSQL, graph query processing, you will study in the big data module which comes in the next semester. Or if you're taking the IoT module that I'm teaching, then we can study some of those new application model in the IoT module. So based on which module is selected, you will study different application models. So as I said, the main innovation behind MapReduce and Apache Hadoop was because we want to solve big data problem. And as you know, the massive big data problem was faced by Google when they had their Google search engine, and they wanted to analyze a lot of search request clickstream analysis, because based on analyzing what links you click on the Google web pages, they get revenue from the advertisement people. So though to create those ads revenue, they need to analyze different clickstream, and based on that requirement, Google engineers, they developed this MapReduce programming model, which was first implemented inside Google Data Center. Then the open source Apache community took that MapReduce programming model and then implemented that in a Hadoop framework, which is an open source implementation of MapReduce programming model. And over the last 5 years, we now have 3 versions of Hadoop: Hadoop 1.0, Hadoop 2.0, Hadoop 3.0, and they all differ the way they manage the different components of the Hadoop cluster using master node and slave node and task tracker. But what is common across those Hadoop 1, 2, 3 is the MapReduce programming model. So the goal of today's lecture is to study that programming model. And it is very important from written exam perspective. So if you look at the last 3-4 year exam paper, there's always a question around the MapReduce programming model. So it's very important for you to understand how MapReduce programming model works and how you can apply that to solve the analytics problem. So we will run through some examples, but based on that example, based on that knowledge, you can be asked questions in the exam to solve similar kind of analytic questions. So what is big data? So we hear this term big data. What actually is big data? So big data means different things to different people. For some people, even 5 gigabytes of data that you can store on your computer could be a big data, because it's not just about the storage, it's also about what you want to search inside the data. So just to give an example, we work with the NHS Trust in Teesside, and they have a database of the patients that includes 5 million patients, and they're stored in a MySQL database. So based on what query they want to do against those 5 million data points, defines their big data. For example, if they want to do a simple query like, what was the last time a patient visited a hospital? This is a very simple query. It's not a big data problem. However, if they want to do a query that says, how many times patient has come to this hospital in the last 10 years, what was their health parameters, how sick they were against certain health indicators. So this kind of query requires a lot of joins on their tables. And if they do for every patient, it takes few hours for them to resolve those kind of queries. So even the small 5 gigabytes of data becomes a big data problem. So the big data is just not about can you store that information on your laptop or desktop. It's not about that. It's about what is the search query you want to do on that data, and whether that search query can be satisfied by one computing node on one laptop in reasonable amount of time. So they are now working with us to scale that search queries across patients using Hadoop cluster. So this is what the example I want to give. Big data is not just about the size, but also about what kind of information you want to filter, search in that big data. But of course, Wikipedia gives much higher level definition, which they say a problem is called big data problem when it becomes very large and complex to be managed by traditional tools such as Microsoft Excel or MySQL Server or MATLAB on single computer or single laptop. That's very abstract or trivial definition. But as I gave an example, that definition doesn't hold just on the size of the data. You may be able to fit 5 gigabytes of data in the main memory available on your laptop, but you're not don't have the computing power to do those complex queries that you want to do on the data. So it's more about, big data is more about what information, what intelligence you want to get from the data rather than about the size of data itself. Of course, size of data can still become a problem if you're a big IT provider like Google and Facebook and Twitter, where you're collecting millions of data streams every minute. So for them, it's all about size, also about querying. But most of other people like NHS Trust and those, it's not so much about the size, but it's more about the queries. So this is very important to understand in context of big data problem. In fact, the evolution of cloud computing was motivated by these big data problems in 2007, and later it became popular for other applications as well because of pay-as-you-go and the economic model that we discussed. But the original motivation for having this big data center was to store, process, and manage this big data produced by companies such as Google. For example, in 2008, they were producing 20 petabytes of data a day. Facebook was producing in 2009 15 terabytes data a day, which increased to 500 terabytes. So you see their data volume is just increasing year by year. And then to store that data, they need a cloud data center. So that leads to evolution of the data center. And once they had the data center, they realized, of course, we can do big data analytics, but along with that, we can support other applications as well that we studied in the previous lecture. And then from there, we had many other innovations like microservices, container, and all those now coming together to support different application models. But real motivation behind having this big data center was to support this data-intensive application. And first of the few data center built by Google and Yahoo was around solving these big data problems. So big data is really big. We are now looking into the scale of zettabyte and yottabyte, and this is just growing more and more with the Internet of Things and mobile phones, and we're generating more and more data. So going forward, they need a lot of expertise in IT industry who can program data center, that's one thing, and who can manage big data on those data centers. That's why if someone has knowledge on Hadoop and MapReduce frameworks, and they know how to deploy and manage those applications on Amazon cloud or in a private cloud, they have a lot of demand because really complicated things to do. Because first of all, you need to know how to handle the big data, and then you also need to know how to process that in an efficient way on cloud data center. And actually, this data is increasing more and more on the internet because of this something like Netflix and Amazon TV on demand, where people are streaming videos all the time. So this data is just increasing with more services moving from traditional televisions to the online television. So this all video content also creates a lot of big data. So as it is shown in this slide, we are generating big data in different facets of our life. We are generating big data when we go to Twitter, we go to Facebook, when we do Google search, when we buy something on Amazon. We are generating big data on the e-commerce side when we buy things from Alibaba or Amazon or eBay. London Stock Exchange and New York Stock Exchange, they are also generating a lot of big data about the stocks and financial services. Actually, Homeland Security is not generating big data. Actually, they are collecting our big data, our activities on Facebook and Twitter and other social media sites. So not all of them are generating, but as far as I know, this Homeland Security, they work with Amazon Data Center to analyze our data, and we don't even know about that. But so some people are generating big data, and some people are just using it to know more about us. So. Yeah, and of course we generate a lot of big data in terms of clickstream analysis when we use search engines such as Google and Bing and others. So really, it's really a lot of data. It's massive big data, and it's a problem for any IT infrastructure to be able to search something inside this big data. That's the main reason why Apache Hadoop and MapReduce framework is so popular? Because it gives you some instrument to be able to not store but process this big data. But of course, you need a lot of intelligence. How do you provision your data into the MapReduce cluster? How do you index it? How do you partition it? What kind of analytic queries you want to program as part of your MapReduce function? So those things, again, come back from your perspective. That's not solved by MapReduce. That is something you have to know. But what MapReduce gives you is a programming environment where you can write your big data queries and run against your big data. So we will try to understand that process through simple examples. So this big data has evolved around 2010, and by 2012 we had a definition, what is a big data. So of course that time there was 3V, but now they also have 5Vs and 6Vs. But on the technical level, there are the 3Vs which are very, which defines the main properties of big data. So first one is variety. So what big data means is now we have data which is coming from multiple sources in multiple formats, structured, semi-structured, and unstructured. For example, when you store data in your MySQL database, it's based on relational schema, so it's classified as a structured data. When you write an email or SMS, it's classified as semi-structured because you have some free text, but along with that you have subjects and date, and so you have some metadata about your emails and SMS. And similarly, there are a lot of unstructured data that we are generating. For example, when we sense the statistics of this building on energy, on humidity, on people presence, on the light. So we are collecting a lot of variety of data. So variety is one problem with the big data. The other problem is the velocity. We are just creating too many data at very high speed. For example, this statistics goes back to 2015 and 2016, where on the average every day people used to tweet 6,000 tweets per second, but sometimes it just peaks to 150,000 tweets per second. Why do you think this peaks? What kind of event leads to this peak in the tweets normally? What could lead to people talking too much? Like Labour Party putting that video on the mirror about the NHS, right? People start talking. So some of these elections, some of these current affairs that happen in the country, people start sharing those videos, and then people start talking about that. That leads to massive influx of the Twitter. Similarly, when we have a new prime minister, then everyone will start talking about it and giving about his opinion. So then somehow Twitter needs certain mechanism to be able to handle from 6,000 data points per second to 150,000 data points per second. So they need to have a proper cloud infrastructure to be able to deal with this heterogeneous, high velocity data streams. And while we have high variety, high velocity, we are storing more and more data, and that leading to data volume. So like as of 2012, Facebook was storing almost 500 terabytes a day, and that all mostly includes the pictures that you share with your friends. There's just too many pictures. And the videos and your chats and all those things, messages, everything is Facebook is storing every day. And of course, Facebook is not allowed to delete your picture, because if they delete your picture, you won't go to Facebook again, you will go to somewhere else. So they just keep storing more and more data, and then that means they need to construct new data centers to store your data. This is what they're doing. But that's the business model, right? They store your picture, they store your information, then they show you advertisement, then they get money, and then they use that money to build more new data center where you store more things. So thing to understand here is big data is a real problem in the IT world, and most of the IT application areas where you work on, you will work on certain aspects of solving big data problem, and you need to understand what are the main properties of big data. That includes volume, variety, and velocity. And then I need to understand what kind of cloud programming framework I can use to process that data and to process. So the thing that we learned today is Hadoop and MapReduce that can only help you process the volume of data, the static data sitting on the storage. It won't help you process the high velocity data. That is done through stream processing that you will study in the big data module in the next semester. The Hadoop will only help you deal with high volume data on a cloud resources. It don't help you deal with the real-time data. So it's also very important to understand which framework is required to process which kind of data. For example, if you want to process high variety data, then Hadoop is not going to help you. You have to come up with some data fusion technique that is independent of stream processing or batch processing. How do you integrate the data? That is based on semantic web and ontologies you develop to integrate those data. So based on what data you have, it's high volume, high velocity, high variety, you need different techniques or different frameworks to solve that problem. So before we start processing the data, the first challenge is data storage, right? So data, as the data storage is a massive issue, the data is getting bigger and bigger, and then, for example, when you upload your pictures to Facebook, right? When you upload your picture to Facebook, you would like that your picture doesn't get lost, right? If you get lost, then you will never go back to the Facebook. So what Facebook might be doing to make sure that your picture, your message are never lost? And they have to do it through across billions of users. They are just replicating your content, right? Replicating content means they are adding more hardware, more CPUs, more storage to data centers. And of course, things fail, so then they have high level of replication to handle those things. So based on what, so because they want to make sure that data that user posts on the Facebook is never lost, that means basically means they need to have more and more IT infrastructure, that is server racks to replicate those content across multiple servers, so that if something fails, you can still recover the data. But then again, it increases the complexity of managing the right infrastructure. That's where the cloud virtualization and those things come into picture, because virtualization can actually help them replicate data at the level of virtual machine and a storage network rather than on the physical server. And as you get more and more server racks and storage racks inside data center, the probability of failures keeps increasing. That means you need more and more sophisticated technique to be able to replicate and make sure the data is available for people who are posting it. So Yahoo was one of the first adopter of the Hadoop cluster and Hadoop and MapReduce programming model. They adopted this around 2007, and they used Hadoop again for the same thing Google are using. That was the click stream analysis. So their revenue model was similar to Google. Whenever a person sends a Yahoo email or goes to a Yahoo search page, and when they want to click something, they want to capture that click, and based on that click, they want to charge their the product or advertisement provider. So mostly in industry, initially it's all based on click stream analysis. Based on when they go to Yahoo or Google web page, which links users are visiting, and based on those links, they want to charge those product provider. And now almost all companies like Facebook, Google, Yahoo, they have this massive Hadoop cluster where they're doing different kinds of analysis. For example, like Facebook must be using it for something else as compared to Twitter, as compared to Google. But most of them are doing clickstream analysis as well, because ad revenue is the main economic model, how they make money. But Facebook might also be doing for image rendering, also be using for video rendering based on other content that you create on those websites. So now we look into what is the main fundamentals behind the MapReduce programming model. So the fundamental behind the MapReduce programming model is divide and conquer. So that basically means if you have a massive data, you have a search query, instead of doing that on one computer, or you divide your data and queries into multiple small components, and then distribute your task across the workers, and then when all worker has finished the task, you just combine all the results and create a result. So it's like, you can say it's similar to the microservice philosophy. When we had a monolithic code, we divide it into decompose into small microservices. Each microservice does a small amount of work, and then we combine results from each of them and create one result. So the basic principle behind MapReduce is based on divide and conquer philosophy. So just to give an example, New York Times, in 2006, they used Hadoop framework to convert 11 million articles that were store as a TIFF image to a PDF files using Hadoop cluster, and they could do the same thing on Amazon Cloud in less than 24 hours by just paying $240. And those 11 million TIFF images was from 1851. So all the additions of New York Times were converted from TIFF image to PDF files using the MapReduce programming models. This is the power of, if they would have done that on traditional few nodes, not using Hadoop cluster, they might have taken years to do this conversion. So this is the power of Hadoop and MapReduce. They can really speed up your job. So what do you think would have been main challenge for New York Times IT engineers? So they had the TIFF image. Now they need to convert that to PDF file. But Hadoop doesn't give you any logic to convert it. So what would have been the main challenge? So Hadoop framework just gives you a way to divide and conquer. Just give you infrastructure where you can divide your work into many computers. But what would be the actual work of the engineers who's working on that project? What kind of programming they would have been required to do? So what would have been the application logic? Because MapReduce doesn't give you application logic. It just gives you a way to program application. Yeah.
Well, they need ways to figure out what character is. It's also ways to divide up the images.
Right. So they need like application logic that divides up the images and converts the images to PDF files. So that application logic, which goes inside the mapper process, has to be written by them. Similarly, the application logic that goes inside the reducer process that combines all the output of PDF for the same file together. So this is something has to be developed by the engineers working in New York Times. That is something not given by the Hadoop framework. Hadoop framework gives you an infrastructure where you can do this kind of divide and conquer algorithm. So then the question comes back to, if you want to use Hadoop framework or MapReduce framework, you need to know how to divide your work into smaller chunks. And this is something is not given. It's not something you can understand. You can get this information from anywhere else. It's something based on your own intelligence. How you are going to decompose a big data problem into something that could be solved by this MapReduce and Hadoop programming model. Obviously, this divide and conquer paradigm is there, but there are a lot of IT challenges that include how do you divide the images, how do you map those images to different nodes, what happens some node is doing this image conversion to PDF, they fail, how do you later combine different parts of images as one PDF, and how do you make sure that everything works fine. So these are some of the things that you need to make sure when you use divide and conquer approach, and these are the things which is made possible by Hadoop framework once you know your application logic. So before we look into the detail of what are the main elements of Hadoop system, let's look down to the main programming abstraction supported by MapReduce. So first one is map, and second one is the reduce. So if you want to program a MapReduce cluster, you have to first understand what's going to be a map function and what's going to be a reduce function. So basically the map function means you take a data, you do certain computation over it. For example, in the case of New York Times, you take a part of the image and convert it into PDF and create a key value pair. And then maybe that different parts of those images are being converted on different mappers. Then the job of reduce page is take those different part of images being converted on different machine and combine them together into one file. So basically, mapper is the abstraction that does processing on the data, and reducer is abstraction that data collection and final aggregation. So these are two primitives. So whenever you have a big data problem, you have to think in terms of map function and reduce function. Of course, there is no one standard way that this is how it should be implemented, this is how it should not be implemented. You can also have multi-level map and reduce as well, based on what is the complexity of your big data problem. But then you always have to think mapper is doing certain computation on the data and doing processing and conversion, and reducing is combining results from multiple mappers. So the fundamental behind the MapReduce is the key value pair. So in case of the images, what could be the key? If you know about keyword, the image ID could be a key, or the date on which that newspaper was published could be the key, and then use that key to divide, to actually convert, to divide that image into multiple parts, and each part will have the same key, and then you divide, each mapper can convert that image file to PDF, and the reducer can take the same keys and combine into one file. So this key value pair is the most important, because key value pair determines how mapper and reducer are working together. So the values with the same key should go to the same reducer so that they can combine different results together. So pretty much MapReduce programming model takes input as a big data file. Based on that, it generates key value pair, which does computation on the data, and then that key value pair is passed to the reducer that aggregates those data together. But of course, the MapReduce framework will not tell you how to decide your keys and key value pair. That's based on your intelligence. But we will show you some examples on how to select a key value pair in case of simple examples, and then you can take that to solve bigger problems. So pretty much both map and reduce phases are based on key value pair. So a mapper takes in a key value pair. For that key, it does all the computation, and that can be done in parallel. And in the parallel, for the same key, those key value pair is passed to the reducer, which aggregates the values across those keys. So this is just two-level mapping from first you divide your data into key value pairs, then the processing happens in parallel, and the value with the same key is given to the same reducer. We aggregate values against those keys. So this is the simple primitive that is used by MapReduce framework. But obviously, the hard challenge is to understand, given my data, what is going to be my key value pair. That's the hard challenge, because it's not same for different applications, different for different applications. So pretty much you give your flat data file to the map function, and based on that, based on your mapping application logic, it creates a key value pair. This is how it works. And then that output is passed to the reduce function that aggregates all the data for that particular key and makes a file. For example, in this case, each of this input could be different part of the images that was converted to PDF. Then the job of the reduce function is to combine those converted small PDF into one big PDF. This is what maybe New York Times engineer would have done. So this shows the whole MapReduce process. So it takes the data, generates key value pair, and based on the key value pair, the shuffling is done. So what shuffling means is the keys, the same keys go to the same reducer. For example, you can say that K1 always comes here, K2 always comes here, K3 comes here, and K1, K3 could be across all these three nodes. So it's job of the Hadoop cluster manager is to copy all those keys and data to the same reducer. So we'll see an example how it is done, but that's the fundamental behind it. After MapReduce is finished, they do the shuffle phase, where the idea is to all the keys and values which are same are copied to the same reducer, where the aggregation can happen. How it's actually done, we'll see with the word count and URL example. So this is how the workflow for MapReduce job works. You get an input. The input is divided into small blocks. That is, you take a big image, you divide it into small images. Then it's given to the mapper processes does the processing on that and creates a key value pair. Then the output with the same keys are sent back to the same reducer within the shuffle process, which is managed by the Hadoop cluster. And then those reducers against the same key that combines all those values together and gives you the final output file. Okay, we'll see some example how this is done in case of if we have few files with different English text. I want to count the same occurrence of same word across those files. What would be my key value pair, and how this could be solved using MapReduce. As I said, if you look at the second point, all of the values with the same key should be presented to a single reducer so that they can combine the results together. That's the key. This is why they use a key value pair, and it will be more clear when we go through the example. Right, so let's say that we have three files, a.text, b.text, c.text, and they all contain some English text, and our job is to count how many times a particular word appears across those files. So in this case, given this problem statement, the key actually is the word, so that I can iterate across all those files and say how many times that word appears. So for example, this is the 3 files. The first file has the word the quick brown fox, the second has the fox and the mouse. It's random text, and now we want to count how many times the appears across the file, how many times brown appears across the file, how many times fox appears across the file. And we want to solve this using MapReduce way of programming application, and then I'll show you how it's done. So this file is given to your MapReduce process, which could be a Hadoop cluster. And then to solve this problem, you have to write this map and reduce function. This is what I called about your application logic. So this is what you have to do. So what it has to do is, it will say that my key is word, and then based on that word, it's going to iterate through each of these and then find a value, and the output will be, okay, the appears once, quick appears once, brown appears once, and fox appears once. And this is based on given that this file is given to mapper 1, this is given to mapper 2, this is given to mapper 3. So each of them will go through this loop based on this logic and make the data structure of key value pair and say how many times each of them happen. And then based on the same key, they will be passed to the reducer, which will combine all those results together. So we'll show how it's done. So this is more of a Java code. If I would try, you can try that as well, but the same logic. So I think this will help you explain more. So you have these 3 files. Each file is given to each different mappers. Right. So as you see, the first mapper found in that a.text, the appears once, brown appears once, fox appears once, and the quick appears once. Right. The second one found the fox appears once, and then these words also appear once. And now, so in this one, you can find out that if you aggregate the key, it appears 2 times. Now the job of the MapReduce process is that we have to map the same key to same reducer. So which word appears twice in this case? Say brown, right? So the brown needs to both brown from mapper 3, and mapper 1 needs to map reducer first. Right. When we do the reduce phase, the unique keys are always passed to the same reducer, and now we have brown 2 times, fox 2 times, and this. You got the feeling how this works, processes. So this is all about key value pair, but of course this case is very simple because it's just word count. But for more complicated cases, we need more complicated key value pair. This is how it works. We try to do one more example. For example, see you are a web portal provider, and you want to know how many people are using which web pages. So what you do in the system, you log the ID of your web page, URL, user ID, time and date. And now what I have to find is which web pages are most popular. So in this case, what will be my key for the mappers? So I want to know which URL has been visited how many times by the users. So in this case, what would be your key? The URL. Any other answer? User ID. But then we have to do multiple aggregation. Right? First, we have to aggregate on the user which URL, and then we say, and we have to check that whether it's unique or not across the users. So maybe having URL as the key is more unique feature. So this is the key, right? When you have this big data, you have to see which is the unique feature in my data, which can be used as a key. That is something important to understand. So in this case, URL is always going to be unique because the user can come many times to the system. So you have to end up that reputation. But if you use URL, then it's fine because that's unique. And then against the URL, say how many users they come, so you can keep adding to the values. So in this case, URL is taken as the key, and the value is how many times user go across those web pages. So this is how it works. This logic is similar to the word count, that each mapper checks how many times URL 1, URL 2, and URL 3 appears. So mapper 1 gets this text, mapper 2 gets this text, mapper 3 gets this text, and then based on this one they say URL appears once, then mapper 2 will say URL 2 appears once, and then mapper 3 also gets URL 1. So that means URL 1 appears 2 2 times. Then the reducer will get both the keys with URL1 and say we'll find out here. Say URL2 appears twice and URL1 appears twice and it appears once. You get the feeling this is how you can do log analysis using Hadoop. These are very simple examples, but from exam perspective, if you understand this mechanism, you can solve the exam question. The exam question could be like, okay, Tesco is having a log of how the product is purchased in different postcodes, and they want to know in that postcode which products are popular. And given that problem statement, write the MapReduce code. So you have to apply this knowledge, decide your key value pair, and then solve the problem. Similarly, NHS Trust want to do analytics on which postcode, which diseases are more common. Then your disease is the key, for example. So this could be different variations of question that could be asked around this MapReduce programming model. But then, of course, if you understand the basic semantics, you can solve all those problems. So if you want to practice those things, you can look at the homework questions and also last 3 years exam papers where the different questions asked around that data analysis problem. So if you solve those, you will be able to think more the diverse ways of applying this MapReduce programming pattern or programming model to solve this data analysis search problems. So this is so MapReduce gives you a way how to program application. Now the next question is, where do we program this? Can we program this in Docker Swarm? So this is just a way, right? This is just the art of programming. This is how you should define your problems as the map, choose your key value pair, and then you have some process like reduce where you pass those things, aggregate those things together. So can you program this in Docker Swarm? Can you write microservices that behaves like a mapper and microservices that behaves like a reducer? Can you do that in Docker Swarm? Based on whatever you have done in your coursework. I know you're not doing anything like that, but just applying your knowledge on microservices and Docker system, can this be done in Docker Swarm or not? You can, but you have to implement all the steps, right? You have to write a mapper code, you need some way to start it, then collect data from there, then do the reduce phase, then reduce microservice, then again. So it's too much work, right? Before you can solve the actual MapReduce problem, you are solving a deployment problem. To simplify that thing, people develop Hadoop because these things can be done by Hadoop itself. So of course, Hadoop can run on traditional virtual machine, or it can also run on Docker as containers and microservices as well. So to help you not to do those basic deployment orchestration, they develop something called Hadoop. But of course, as you said, it's quite possible to write all this and deploy those microservices yourself, but you're wasting a lot of time deploying container with mapper and collect data, put a reducer, and before your application gets answered, it'll be a few months before you solve this problem. So all those things I described is solved by a framework called Apache Hadoop. So it's free to use tool. You can go and download it. There are many versions of Hadoop. One that runs on Amazon Cloud is called Elastic MapReduce, or one that runs on virtual machines, one that runs on your Docker cluster. So you can download any of the version based on where you want to run. I would advise, if you really want to know more about this, you should download the version that runs on Docker and try it on your laptop, having 2-3 nodes, and just see how it works. That will give you a better feeling of how actually this MapReduce programming model is different from what you're doing in your coursework. That gives you more broader understanding of the problem. So Hadoop actually solves a lot of problem I described. It gives you a nice functional programming interface where you can define your map and reduce logic. So in that environment, you can define that logic. It gives you a fault-tolerant data storage. For example, if you store something on the Hadoop cluster, if something fails, this Hadoop has replication across at least 3 nodes, so it has ability to recover your data as well. So for example, if you're implementing this on your own Docker, you have to implement replication as well. That's again very complicated, but that thing is solved by Hadoop framework. It gives you ability to start MapReduce process in parallel. So it will do it automatically. It gives you ability to to copy data from mappers to the reducer with the same key. It's done automatically by the framework. You don't have to worry. As long as you select your key value pair carefully, it will do it by itself. It can do the network I/O and disk scheduling in a very efficient way. And it can also keep track of monitoring the status of your running jobs as well. So most of the fundamental thing of resource management is done by Hadoop framework, so you don't have to worry about that. So one thing you need to worry about that is what is my data analysis logic that goes in the MapReduce process. So that's something you can focus and develop a smart technique for that, rather than worrying about the small, low-level stuff, which is actually managed by the Hadoop cluster. So of course, if you are this guy, this programmer, you don't have to worry about where my data is located, how to handle resource failures, how to handle if data is lost, you do have to worry how to divide computation and the logic, but you don't have to worry how to start the mappers. That's what it means. And you also don't have to worry how to scale the infrastructure, because you just can go to configuration file and say, now instead of 2 mappers, I need 10 mappers. It will automatically scale infrastructure. So those things is automated by Apache Hadoop framework. So yeah, that's what happens when you enter the Apache ecosystem. So Apache Hadoop consists of many things. For example, it has a file system, it has a MapReduce framework, it has a Hive framework that can take your structured SQL data and put in the MapReduce format. You have data orchestrator, and I think this ecosystem now has more than 1,000 projects that can support different types of data analysis. So this gets more and more complicated. But the focus of this lecture is just to understand the 2 main layers of the Hadoop framework. The first is the storage layer. So this is one of the main layers you need to understand, the file system where your data is stored. The name for that is Hadoop distributed file system. So as the name implies, it's a file system that is not sitting on one node or one VM or one container. It is distributed across the whole cluster. So normally, a Hadoop cluster means it's a collection of many machines which can be virtualized either using virtual machine hypervisor or containers. And across all those containers, you manage, you store, index your data, and copy your data using a file system called Hadoop distributed file system. And that comes with the default installation of your Hadoop framework, so you don't have to worry about that. So HDFS layer takes care of the storage, and then the MapReduce layer takes care of the computation, where you actually program your map function, reduce function, and the shuffle logic. So these are the 2 main layers you need to be worried about when you deal with the MapReduce. And of course, to make both those abstraction, compute, and storage work, there are many components in the Hadoop system that we will study after the break.